Anything from 37 to 41? All right, if there are no questions, we will move on to page 51.
Did we just skip like half of it?
No, it's just those are just work. Those are just exercises. So yeah, we skipped some exercises, but you'll go back and do them. Okay, two main types of energy. We have kinetic energy, which can be abbreviated KE, and we have potential energy, which can be abbreviated PE. Oh, sorry, there is some physics and chemistry. Hopefully, by this point in your science life, you know that kinetic energy is the energy of motion, and that potential energy is energy that is stored. Do you guys know the law of conservation of energy?
I forgot. Oh, it either can be created or destroyed.
It cannot be created, it cannot be destroyed, it can only be converted from one form to another form. Okay, so the total energy stays the same. Total energy will always stay the same. Kinetic energy can be transformed into potential energy. Potential energy can be just transformed into potential energy, backwards, forwards, whatever. What is the unit of energy? Unit. What do we measure it in?
Joules.
Joules, okay? So it's either joules or it can also be kilojoules. We often use kilojoules in chemistry. So kinetic energy in chemistry. We are mostly talking about the motion of molecules. Remember, my abbreviation for molecules is MC. And there are three types of molecular motion. Thank you.
More than one, right?
No, just one. Uh-oh. There are three main types of molecular motion. There is, that goes there, that can go there. Perfect, thank you so much. Vibrational, which means if you have, say, a carbon dioxide molecule, there are several types of vibrational motion. You can have, if this is the carbon and these are the oxygens, you can have vibrational motion in terms of bending. The molecule can go like this, okay? It can do symmetric stretching. It can go like this. Or it can do asymmetric stretching where it goes like this, okay? So any of those are methods of vibration of the molecule. There's also rotational. So you can have the thing spinning like this. Okay, I can't do it, but you know, if I was to like do a, right, more like this, yes, that would be another type of rotational motion. So we have vibrationals, we have rotational, and we have translational. And that should be in the cell hotel. Oh, it was your computer, never mind. Okay, translational just means it's moving through space, okay? And you can have something that is rotating and vibrating and translational motion. You can be doing all of them at the same time, which is what molecules mostly do. all of these together contribute to the kinetic energy of the molecules. The more a molecule does any of these motions, the more kinetic energy it has. The faster a molecule moves in any of these ways, the more kinetic energy it has. Is good? Basically, more movement, more kinetic energy. Temperature. You have to know this. You memorize this. Temperature is a measure of the average kinetic energy. So temperature can just be thought of as the average kinetic energy. So if you have faster molecules, you have more kinetic energy, and that's going to be a higher temperature. If you have slower molecules, you will have less kinetic energy, which means you have a lower temperature. So that's sort of kinetic energy in a nutshell. Potential energy, it's the energy that is stored in the atoms and the bonds. So potential energy is energy stored in atoms and their bonds. And it can be released or absorbed by various chemical reactions. So if you have a high potential energy, they are less stable. If you have a low potential energy, those are more stable. So if you think about a ball on a hill, the ball at the top of the hill, is that at a high potential energy or low potential energy? That's at a high potential energy. Is it stable there? Is it going to stay there forever? No. Given any opportunity, it's going to do what? Roll down the hill, okay? It is unstable. If we have a ball at the bottom of a hill, this is at a low potential energy, and that is stable. Nature is always going to tend towards low potential energy, stable. That's how things naturally go, okay? Low potential energy, high stability. Maybe I should just say very stable. Or just stable. So now that we've got an idea of what kinetic energy, what potential energy is, we're going to talk about energy transformations. If we take kinetic energy and we transform it into potential energy, what's going to happen to the amount of kinetic energy? Yeah, the amount of kinetic energy decreases, the amount of potential energy increases. And if the amount of kinetic energy decreases, what else decreases? Sorry? Temperature, yes. I'm sorry. Thank you very much for articulating. Sometimes I just, I don't know. Even when I'm watching TV and stuff, I have trouble understanding what they're saying. I always have the closed captions on, so, So therefore, the temperature decreases, the particles move more slowly. What happens to the total amount of energy? Stays the same. If we take potential energy and we convert it into kinetic energy, if we transform it into kinetic energy, what has happened to the amount of kinetic energy? Increase or decrease? Increased. And therefore, what's going to happen to the temperature? Temperature is going to increase. It's going to get warmer. And the particles will move faster. But again, the total energy is staying the same. And the potential energy, what happens to our amount of potential energy? Our potential energy decreases. So let's say that we have some reactants in a chemical reaction, okay? And these reactants have 2 kilojoules of potential energy. Okay, that's just how much they have. That is their nature, okay? We have some products, and the products have 12 kilojoules of potential energy. What that means is that you must have your reactants, which have 2 kilojoules of potential energy, your products, which have 12 kilojoules of potential energy. And remember, energy is neither created nor destroyed. So if we have 12 kilojoules on the right-hand side, how many kilojoules do we have to have in the reactants? 12 kilojoules. Right now, we only have 2 kilojoules of potential energy. So we also have to have 10 kilojoules of what type of energy? Kinetic energy. Okay, so that's 10 kilojoules of kinetic energy. So that is 12 kilojoules on the left, 12 kilojoules on the right. So you're always going to have the same amount on the left and the right. When you see an energy term, the energy term is always kinetic energy. So in this reaction, did we transform potential energy into kinetic energy, or did we transform kinetic energy into potential energy? In the above reaction, did we transform potential energy to kinetic energy, or kinetic energy to just over here? All right. So we have which one did we do? Sorry, I got distracted. Talk with your partner. Did we go PE to KE, or did we go KE to PE? We have more potential energy than we did before, right? And that kinetic energy got used up What does it get used up? It gets turned into potential energy. So we took kinetic energy and we turned it into potential energy. So what happened to the amount of kinetic energy? Amount of kinetic energy decreases. And that means that what's going to happen to our temperature? Particles are moving slower. And if the particles are moving slower and the kinetic energy has decreased, what has happened to our temperature? Temperature has gone down. Okay? Now, people sometimes get confused because sometimes we call this the heat term. Okay, and they're like, oh, you added heat. It must have gotten hotter. But that's not what the question is. That's not what the reaction actually says. It actually says we took 10 kilojoules of heat and we turned it into potential energy. So now we actually have less heat than before. Okay, so it actually gets cooler. So when you see plus 10 kilojoules of heat, don't think I'm adding in 10 kilojoules, thinking I'm taking 10 kilojoules of heat and I'm using it up. So everything's going to be cooler than it was before. Okay. By the way, do you guys recognize from that reaction whether that is endothermic or exothermic? What are those two terms mean? Okay, well, let's keep going before we talk about that. Okay. Pardon me?
Well, kinetic energy is used here, right?
Yeah.
So that's going to be endothermic.
Yes. Okay. So this is just an expansion of what we talked about before. We've got our potential energy here. We got our potential energy here. We got our kinetic energy here.
Well, that's what we did here, right?
Yeah, we did that there. I've just got it over here, but the two are the same. Total energy before is equal to the total energy afterwards. And we can graph this on a potential energy diagram. Okay, so graphically, what that's going to look like, we have our potential energy on the y-axis. And we're starting at 2 kilojoules for our reactants. So here's our reactants down here. And our products have 12 kilojoules of potential energy. So they are up there. So in between the reactants and the products, we have to go up. Where does that extra energy come from? It comes from the kinetic energy. This extra energy here comes from kinetic energy being transformed into potential energy. So you can visualize this as kinetic energy comes in.
Is it possible to tell if it's gonna be kinetic energy to be used or not be used without fixing the?
You need to either have a graph or an equation or a change in enthalpy, which is what we call the change in potential energy. So you have to be given something about the question, okay? So eventually when we draw these, we're not going to draw the little squiggly kinetic energy going in arrow, all right? That's just so you can help visualize that the kinetic energy is going in. Now, if kinetic energy is going in, we call that an endothermic reaction, okay? So the kinetic energy goes in, that is endothermic. But don't forget, when it goes in, it is then transformed into potential energy. So endothermic reactions, do endothermic reactions get warmer or cooler? They get cooler. So it gets cooler as Ke changes into potential energy. And so if you have a potential energy diagram that goes up, that is going to be an endothermic reaction. Now let's think about it. Lots of buildings, when you go into them, do you normally walk like downstairs to get into a building, or do you normally walk upstairs to get into a building?
Upstairs.
Usually you walk upstairs. I'm not saying all buildings. I know there's like, little walk downs or whatever, but very often there's steps to get up to a building. So you can think of this diagram, a potential energy diagram, where the stairs go up, you are entering, so that's going to be endothermic. So if the graph goes up, if the potential energy graph goes up, that is endothermic. Because stairs go up when you enter a building. So that's one way to recognize a potential, an endothermic reaction, is that the stairs go up. The other way to recognize an endothermic reaction is that the energy term is in the products or reactants. Energy term is in the reactants. Energy enters the equation. So now you have two ways of knowing that a reaction is endothermic. You can either see, I've got A plus kilojoules goes to B. There's my energy term in the reactants. Energy is entering, or my potential energy diagram goes up. That's an endothermic reaction. Or if it says it gets cooler, you also know that it is endothermic. All right, next example. You have some reactants. Now the reactants have 9 kilojoules of potential energy. And your products have only 1 kilojoule of potential energy. So for the kilojoules to be equal on both sides, we need an extra 8 kilojoules on the right-hand side. What kind of energy is that going to be? That is kinetic energy. So what has happened is we've transformed some of the potential energy has transformed into kinetic energy. Are our particles moving faster or slower now? Particles move faster. Is it going to feel warmer or colder? It's going to feel warmer. The temperature increases. And you'll notice here that our energy term is in the products. Is the energy term entering the equation or exiting the equation?
Exiting.
It is exiting the equation. EQN for equation. And if energy exits the equation, it's not endothermic, it is exothermic. The term therm has to do with heat. So exothermic, exit heat. The term endothermic, enter heat. Okay?
Maybe.
How many of you did this last year? Good stuff. If you didn't, it's okay. Is it ringing bells? Is it coming back? A little bit? Yeah? Okay. No worries. We're taking it from as though you didn't know it. Okay? So if it's been since, last September or whatever, that's all right. All right. So this is just, again, showing that we have our 9 kilojoules of potential energy in our reactants, 1 kilojoule of potential energy in the products, and then we would have to have 8 kilojoules of kinetic energy in the products so that it both equals 9. Total energy before equals total energy after. On our potential energy diagram, if you exit a building, Which way do the stairs go? The stairs go down. And you can see on this potential energy diagram for an exothermic reaction, the stairs go down, or the graph goes down. A potential energy graph for an exothermic reaction goes down. Once again, potential energy is on our y-axis. This time we are starting high and we finish low. So our potential energy decreases. Where does that extra energy go? It comes out as kinetic energy, as heat. It is transformed into kinetic energy, and the kinetic energy comes out and that increases the temperature. Is good? Okay. So 2 ways to recognize a reaction is exothermic. You've got the energy term in the products, or you have it going downhill. All right, so there's like a little reading check here. We're not going to do that. You're going to do that at home. And we're going to move on to enthalpy, which is on page 56. For the purposes of chemistry 11, enthalpy can be thought of as chemical potential energy. So enthalpy is approximately the same as potential energy in chemistry. That's not its definition. If you define it as potential energy, you're wrong. However,
is it partially right though?
it's a little bit right, but not really. I'll read you the actual definition of enthalpy, and you can tell me whether you want to learn that one or whether you just want to think of it this way. You will not actually be asked to define enthalpy, so it's okay that you just think about it as chemical potential energy. This is the actual definition of enthalpy. If I can find my glossary here. Enthalpy, a quantity defined by the relationship H equals E plus PV. The enthalpy change, delta H for a reaction that occurs at constant pressure, is the heat evolved or absorbed in the reaction. Delta H is equal to QP. Anyone want to learn it that way?
Basically potential energy.
It's a mathematical definition, okay? And it has to do with P delta V work, and you guys don't know what that is. So we're just going to leave that aside and think of it as potential energy. Does that make sense? Okay, cool. Now, enthalpy, I guess we couldn't call it E because E is energy, so we picked a random letter in the middle of the word, and we said H will stand for enthalpy. Did you learn of the term enthalpy last year? No? Okay, that's all right. No worries. You're learning it this year. It's essentially the same as the potential energy. So just a new word for it. Hopefully from math, you know that the symbol delta, that's our Greek letter delta. And what does it mean? Change in. Okay? Often when we are looking at enthalpy, we are looking at a change in enthalpy, because remember, our graph either goes down if it's exothermic, if we have a negative change, or it goes And change in enthalpy is symbolized as delta H. So in an endothermic reaction,
So we could write change in H as change in P.
no.
Oh.
Okay, write it. Oh, well, I suppose you could, but don't. Okay, yeah. So in an endothermic reaction, the change in enthalpy is positive. That's because in an endothermic reaction, kinetic energy is transformed into potential energy. And that means that our kinetic energy goes down and our potential energy goes up. And if our potential energy goes up, that means our enthalpy goes up, because you can think of enthalpy and potential energy as essentially the same thing. Okay, so potential energy increases, enthalpy increases. Therefore, the change in enthalpy is positive. So now you have three ways of recognizing an endothermic reaction. You know that for an endothermic reaction, number one, change in enthalpy is positive. Number two, the graph goes up. And number three, the energy term is in the reactants. Those are three ways you can recognize that something is endothermic. If you are given one of those, you should be able to write the other two. Does that make sense? So if I give you something where the kilojoule term is in the reactants, you should be able to draw a graph that goes up. You should be able to state that the change in enthalpy, delta H, is positive. Okay? For an exothermic reaction, our potential energy is transformed into kinetic energy. So potential energy goes down. So potential energy is decreasing. Potential energy and enthalpy are essentially the same. So if potential energy decreases, that means enthalpy also decreases. And if it's decreasing, then the change is negative. So for an exothermic reaction, you should know that number one, change in enthalpy, delta H, is negative. You should be able to draw a graph, a potential energy graph. And what direction do the stairs go? They go down. And thirdly, you should be able to write an equation where your reactants go to products and your energy term is in the products. You can think it through and understand it. That's the best way of learning it. Okay? Think it through and understand it. But if you're stuck, you can memorize it. Okay? Not the best way of learning it, because things that you just memorize without understanding them, they have a tendency to fall out your ears. Yes? They're there for a little while and then they're gone. Where'd they go? Yes? So try to understand it. Okay? So this energy term, we sometimes call it the heat term. That's our kilojoules. That's our kinetic energy term. What type of a reaction is this one? Is this endothermic or exothermic? This is exothermic. The heat has exited the equation. All right. So if we wanted to graph this, try and draw yourself a little mini graph of what that would look like. Pardon me? We will do kinetic energy later, but it has a different purpose behind it. Okay?
But when the heat exits, the heat still goes up at the end product.
Heat is kinetic energy. What is this graph?
So it goes like from high to low.
This graph is potential energy. So we just ignore the kinetic energy. The kinetic energy is not on this graph. Okay? So what you should have is you should have it starting high and finishing low. All right? That's what your graph should look like. And what do we have along the x-axis? Usually this is progress of the reaction. So it just tells you as the reaction proceeds, as it goes along. You could write time, but then it actually implies that we know something about the time, which we don't really. This is more of a qualitative graph than a very quantitative graph. And what is delta H for this reaction? Is it positive or negative? Tell your partner, is change in enthalpy positive or negative?
No.
Change in enthalpy is negative. Okay, and if you were to actually draw your change in enthalpy on this diagram, what it would look like is we would start at the level of the reactants. That's our start. And we would finish at the level of the products. And that would be our change in enthalpy. And you'll notice it is going down. That means it is negative. How are we feeling about graphs?
I don't like graphs.
Thumbs up, thumbs down, thumbs in the middle. How are we feeling about these graphs? Thumbs up and in the middle. Okay, I can take that. We can work on them a little bit. Very good. All right. Now we have, oh, this is just showing you what we just did. Okay, this is just more, and you can see the kinetic energy comes out. Potential energy was transformed into kinetic energy. You're not going to have to show this arrow. In fact, you shouldn't show this arrow. Shouldn't.
Is it like incorrect?
It just looks like it's just there as a visualization for you when you first start, but nobody shows that arrow ever. So just, you know, if you want to show it, that's okay, but you shouldn't show this arrow on tests. If you are asked to label the change in enthalpy, it has to start at the level of the reactants and it needs to finish at the level of the products. It would not be okay to draw your arrow like this. Why is that arrow not okay for the change in enthalpy? It's the wrong size. It doesn't actually represent how much energy is lost. So this is not an okay arrow for delta H.
It just shows that going down, but not where.
Right. The amount is wrong. The amount is wrong. So start at the start, finish at the finish. Make sure you like touch those lines, okay? Okay, and we know this reaction is endo or exothermic. This one is exothermic. And the temperature, therefore, must be increasing or decreasing? Increasing. There are two ways to write a reaction to show that it is exothermic. You can write it with the heat term, exiting. Or, instead of writing the heat term in the reaction, you can write the change in enthalpy beside the reaction. Okay? Now, I want you to notice delta H has a negative sign. Does our heat term have a negative sign? No, because it's coming out. We wouldn't say negative 5,000 kilojoules come out, because that doesn't make any sense. So there's no negative sign here. The heat term is always positive in the equation, okay? It's only when you write it as a delta H that it needs a sign. Is good? Okay. What kind of a reaction is this one? Tell your partner. I'm going to start drawing cards, because that'll be fun. You guys are yellow. Yeah. Is this an endo or an exothermic reaction? Should the graph go up or down? Is delta H positive or negative? Does the graph go up or down? Is delta H positive or negative? That doesn't look like graph. Looks like some weird word. Okay, Sambed. Endothermic, yes. Does the graph go up or down, James? It goes up. Is delta H positive or negative, Eric? It's okay to say pass if you have been startled. You can pass. Owen? It is positive, yes. Okay. All right. So if the graph goes up, you can say, what direction would my arrow go to get from my reactants to my products? Okay, and so the arrow would go up. Therefore, the change in enthalpy is positive. Okay, so that's going to help you. If you know that endo, the graph goes up, that's going to help you determine the sign of delta H. Okay. There's our graph. Kinetic energy comes in. It's transformed into potential energy. Blah, 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 blah. Heat term is on the left side. We've talked about that already. And then we've got some exercises. So I think what I'm going to do at this point is we have how many minutes? We got 15 minutes. Actually, you know what? I would like you to work on. You know what? I'd actually rather you guys do this one first. So let's do pages 59 and 60 first. Because we've just done that, it'll be fresh in your head.
We just circle it. Yeah.
And then we'll add on to that.
It'll be harder. But this part is going to be like really, but the other part is going to be like just a lot of memorizing. Yeah, that's like escaping the matrix. And they think we just